So I'll be presenting Swiss IMO Selection 2020 Problem 8. It was a geometry problem that appeared 4 weeks ago. So first of all, I'll introduce some background. So the tangent perpendicular to radius, the Thales circle, the Center Lemma, and the PowerPoint. So this might be very simple for some people, but I'll just go through it quickly. So if we have a tangent to a circle and AB a diameter and TB a tangent, then this angle will be 90. The converse is also true. So like if we have TB a tangent and angle TBA is 90, then AB will be a diameter and so on. So if AB is a diameter and this angle is 90, then this will be a tangent. Then the Thales circle. So if you have AB a diameter of a circle and C a point on this circle, then angle ACB will be 90 degrees, as this corresponds to half of the whole circle, which is 360 over 4 is 90. So now the in-center lemma, also known as the in-center x-center lemma, but we don't need the x-center part. So if we have I, the in-center of a triangle, which is the intersection of the angle bisectors, and D, midpoint of arc BC, then we're going to have, so D is the midpoint of this arc, then we'll have that D is the center of the circumcircle of BIC. So I'll quickly prove this. So we know, let's just call this angle alpha, this angle beta, and this angle gamma. So I'll just mark these angles. Okay, so we have that. We don't need the gamma part because with an analogous argument we'll just finish. So we have that BACD is cyclic, of course, as the points lie in this circle. So angle DAC is angle DBC. We can just call this alpha over 2 as well. And also angle BID is exterior. Yes, is exterior to the triangle BAI. So this angle will just be angle ABI plus angle BAI. So this will just be beta plus alpha over 2, alpha plus beta over 2. As it's supplementary to this angle, and this angle is 180 minus the sum of these two angles, of course. But now angle DBI is alpha plus beta over 2, but also angle BID is alpha plus beta over 2. Therefore, these two angles are equal, and therefore BD equals DI. Now with an analogous argument, we can just conclude that this angle here equals this angle. They're both going to be alpha plus gamma over 2. Therefore, this is also equal to that. And therefore, D is the center of the circumcircle of BIC. This theorem will be very important for this problem, and all the points in the problem will revolve around this point D. So therefore, it's very important that you understand this. Okay. So now I'll present the power P, which is another theorem we're going to use a lot in this problem. So if we have PAB collinear and PCD collinear such that ABDC is cyclic, then we have, I'm not going to reveal the statement, some of you might know, but I'll lead up to it. So if we call angle ABD beta, then this is of course 180 minus beta, as this quadrilateral is cyclic, and this is supplementary to angle ACD, therefore this is beta. So, and this angle is shared in both triangle APC and BPD, therefore we have that triangle PAC is similar to triangle PDB, as they share an angle and, well, two angles. Now we write as a ratio, so PA over PC is equal to PD over PB, and multiplying both sides by PB and PC, we get that PA times PB equals PC times PD. So oh, I'm getting the lines again. Whatever.
Oh.
Yeah. Anyways, okay, I'll just continue and remove them once in a while. So
Yeah.
I'll just go through one of the degenerate cases of the power of point. So if we have C equals D here, then we have that PC is of course a tangent, and then we can replace D by C and we get PA times PB equals PC squared. And well, we will use this statement as well. I didn't have to show it, but it's worth showing. So, and we will also use the converse, so that if PA times PB equals PC squared and PA and B are collinear, then PC will be tangent to the circumcircle of ABC. So now let's start the problem. So we start with the circumcircle of ABC. Then we introduce I, the incenter of this triangle ABC, and then we introduce F, which is BC intersection with the perpendicular to AI through I. So FI will be perpendicular to AI, and F will also be on BC. Then we introduce M, the midpoint of the arc BC containing A, so the larger arc. Why are these lines here? Okay. And then we also introduce N, which is MI intersection with the circumcircle of BIC. So I'll always have the points up over here so that you can see the definitions. And our goal is to prove that Fn is tangent to the circumcircle of BIC. So so we have a drawing here. So here it's very important that we introduce this point D as, well, you will see. So we let D be the midpoint of the arc BC, not equal to M, so it doesn't contain, this arc BC won't contain A. Now it's very easy to observe that DM is a diameter of the circumcircle of ABC, as, well, we take BC, a chord, and then we take the two midpoints of the arcs, and, well, this will just be half of the circle at the end, and therefore DM will be a diameter. But this is not the reason why we introduced D. The reason why we introduced D is because D will be the center, the circumcenter of the triangle BIC with the in-center lemma, well, which we had proven. And furthermore, well, now we can relate D to BICN as it's the center of this quadrilateral, or the circle through this quadrilateral, and A as AID are collinear, and M as DM is a diameter. So now we want to bring F into the picture, and we do this through two steps. But the first one is we prove that Fi is tangent to this circle, which is quite obvious with the tangent perpendicular to radius, as Di is a radius of this triangle circle with the in-center lemma, and also angle FID is 90 degrees, and therefore Fi will be tangent to this circle. So now these are the easy steps which most people got, but then it becomes quite unclear, and you have many possible approaches here. So one approach is to prove that FD is the angle bisector of angle IFN, which leads to Fn equals Fi as, well, we have that dn equals di with the in-center lemma, and it's quite easy to get that Fn equals Fi and actually finish from this, as Fn equals, if Fn equals Fi, and if we assume that Fn is not a tangent to this circle, then we can introduce n prime, which, so we can introduce this point n prime here, such that Fn prime is tangent to this circle. But now Fn prime will of course equal Fi, as, well, but there are many ways to show this, but just the power of point will suffice, as the power of F with respect to this circle will be Fi squared and Fn prime squared, and therefore Fi will equal Fn prime, but Fi also equals Fn. So now f is equidistant from n prime, n, and I, and therefore f is the center of the circle. So f will be equidistant from 3 points, and therefore it will be the circumcenter of this triangle. But we already know that n prime I lie in the circle with center D, and D of course doesn't equal f, as well f is on BC but D is not, and therefore we have that Fn equals Fi suffices, as we get a contradiction. And finally, another possible approach is to prove that angle FND is 90 degrees. These lines. As with the tangent perpendicular to radius, we'll have that Fn is a tangent as Nd is a radius, and this angle will be 90 using the converse of this statement. We will be able to finish. So here, as I said, we have 6 points that are related to D out of the 7 on the picture, excluding D, of course. So now we want to relate F and D somehow, and we can do this. Well, so in the competition, you most likely intersect these points if you want to intersect as in connect them. Connect these points to somehow relate them together, and in doing so, you most likely realize that MI, FD, and the circle intersect at a point. So now we want to prove this, and there's a pretty nice way of doing this. Namely, we introduce R to be FD intersection with MI, and R prime, which will be FD intersection with the circle. So R won't necessarily be on the circle, but R prime will. So if we prove R equals R prime, then R will be on the circle as R prime is, and they're equal. So now we know that Fi is a tangent to the circumcircle of BIC. And therefore, with the power of a point statement, we have that Fi squared equals Fb times Fc. Do you also see these lines? On my...
Yeah.
Yes, I don't know why they're there.
Yeah, it's not me. It's not me.
Whatever happened, right? I never seen things like that.
You can annotate on other people's things. And
Yeah, no, that's what I was thinking when it kept happening to me.
Yeah, like, can
I think you can
that?
block. I think you can, like, I was just thinking.
Try to block, yeah, because it's really difficult to concentrate.
Yes. And for me as well.
Yeah.
It's not annotate.
Like, maybe if you go into the screen share settings or something, you can, like, not allow other people to annotate.
Be under more, but
Why don't you just not use the pointer? Just disable pointer.
possibly disappears. But the pointer is from my software, not Zoom. From the software I'm using to create the presentation.
No, and it was happening to me as well. So
Yeah, but I'm not sure it relates to Zoom.
Oh, it doesn't relate to Zoom, but it's.
I've never seen it before. I don't know.
But
We had it like in the last presentation as well.
Okay, I did, I think. Disable participant annotation.
Okay.
Okay, it should be good now. So,
where did you find it? Just for my presentations later on?
actually, you can't see that part of my screen because I don't know why. But so when you're screen sharing, you go on more. So that's when you go to the top, there'll be like mute, stop video, participant, new share, etc. And then you go to more, and then there's allow participants to annotate or disable.
Okay.
Yes, and then you pick
Okay.
latter. Okay, so now is there something unclear, because there might be, as there were so many.
Can you repeat again the definition of R and R prime?
Yes, so R will be, so I'll just say what we established. We established that Fi is tangent, as this is 90 degrees and this is a radius with the first theorem I presented. that D is the center of this circle with the in-center lemma, that dm is a diameter, which is quite easy conceptually. Then what else? I think that's it actually. And so now we just, and the definitions of f and etc. are up here, so you can just look at them later. So here we introduce r, which is mi intersection with the line fd, and r prime, which will be fd intersection with the circle. There's this case where fd intersection with the circle, second intersection with the circle, doesn't exist, so fd is tangent, but I think it's pretty easy to rule out, and I won't show it, so yeah. So we introduced these 2 points, and it actually suffices to prove that r equals r. To prove that r is on the circumcircle of ABC, it suffices to prove r equals r prime, because, well, r prime is on this circle, and if they're equal, r will also be on the circle. So this is what we want to prove, that mi, fd, and the circle intersect at this point r. So now we introduced these 2 points, and then now we realize that fi squared is fb times fc, with the power of a point, as fi is tangent to the circumcircle of BIC, and BC are of course on this circle, and FB and C are collinear. But now when you look closely, you realize that B, C, D, R prime are also cyclic, and F, R prime, D are collinear, as well as FBC of course, and therefore FB times FC equals FR prime times FD. So we get two things that are equal to FB times FC, and when we equate them, we get FI squared equals FI squared equals FR prime times FD. But now using the converse of the power of point, we get FR prime and FD are collinear, as well as FR prime times FD equals FI squared. Therefore, FI will be tangent to the circumcircle of I, R prime D at I. So, okay, so we get something like this. So this is tangent here, because fi squared is equal to fr prime times, okay, that's a bad line, fr prime times fd. And now we have that di is a diameter, as angle FID is 90 degrees, and fi is tangent to the circumcircle of I, R prime D at I. And this just uses the tangent perpendicular to radius. So we have a tangent, is perpendicular to something, and it will be the radius, as it's an if and only if statement. So di will be a diameter of this circle. And now we have that angle I, R prime D is 90 degrees. This is the only time where we use the Dallas circle, as di is a diameter of the circumcircle of D, R prime I. And therefore angle I, R prime D will be 90. So now we introduce this point M prime, which will be R prime I intersection with M prime. I didn't introduce it because it kind of spoils some stuff, I guess. So we have that this is 90, but sorry for the bad line. Just pretend this is a line, and that this is 90 degrees. So now we have M prime, R prime D on the circumcircle of ABC, such that angle D, R prime, M prime is 90 degrees. But now, again using the Dallas circle, okay, 2 times, we get that DM prime is, a diameter, as this is 90 degrees. But we already know DM is a diameter, therefore M must equal M prime. So now,
Sorry, why dm prime is a diameter?
as angle M R prime D is 90 degrees, and I proved that I didn't prove it, but I stated the Dallas circle theorem. So this will just correspond to half of the whole circle.
Okay.
Yes. So now, well, as I said, dm prime will be a diameter, and therefore dm being a diameter as well means that M prime will be M, as there's only one point diametrically opposite to them in this circle, a D, I mean. So now we have that R prime, I, and M are collinear, as R prime, I, and M prime were collinear, and M prime is M. Therefore, MI, R prime, and R, I, M are collinear. So these two lines, R prime, I, M, and M, I, R are lines. So like, okay, I'll state this again. So R prime, I, and M are collinear, as well as R, I, M. But now there are 2 points in which MI intersects the line FD. And this is a contradiction. So therefore, R must equal R prime, as like 2 lines can't intersect at 2 points. So now we have that R is on the circumcircle of ABC, as well as angle IR prime D, which will be angle IRD, as R is equal to R prime, being 90. So now we can move on to the finishing up the proof section. So we have angle IRD equals 90, of course, as angle R prime D equals 90, as I established earlier, and R equals R prime, of course. And moreover, DI equals DN because of the in-center lemma, as D is the center of the circumcircle of NBIC. So now we can look at this more simplified drawing, also this, but here we can clearly see that just using these 2 bullet points, we can conclude that NI, FD is the perpendicular bisector of NI, as well it of course is perpendicular to this, as angle IRD is 90, but also ID equals DN, and therefore this will also equal that, and therefore it will be the perpendicular bisector, which will be enough to conclude that Fi equals Fn. And I established that this suffices, proving that I proved that this suffices to prove the initial in our goal, which was to prove that Fn is tangent to this circle. So yes, we're done then.
Okay, well, thanks a lot.
Thank you, thank you, thank you.
Any questions?
Yes, I have a question. So the first part with introducing D is more or less common, and you do it often in Olympiad. But here, which was easier or harder for you, Bora, to sniff that DF and MI intersect on that circle, or to prove that R coincides with R prime? These were the 2 hard steps. I wonder which one was harder.
Actually, I made a mistake during the Olympiad. I thought that I finished, but I hadn't actually. I had pretty much assumed the problem, and then I was done. So like I kind of no, I finished after the very last slide I did, and then I somehow made a mistake with angle IR prime D equals 90. I kind of assumed this somehow, and then I was done. But then I realized I had made a mistake. So I guess proving R equals R prime was the most difficult. But because otherwise, if you just introduce FD, you pretty easily see that MI FD can intersect on this circle, because you already have MI N, so you already have this point N. So they do intersect somewhere on your drawing, and then you see that it's actually on the circle.
I see. So in a way, working backwards, if the problem is true and Fi is equal to Fn, then it must be that they intersect on the circle.
Yes,
and
so
the hardest step was to prove
see that they do, and then you just check if this works, like if the problem holds, if this holds, and then you prove this, and then proving R equals R prime is kind of difficult, but not very. You just use PowerPoint like 1, 2, 3, 4 times, and then tell a circle twice, and then you're done. Yeah.
Okay, well, more questions? Well, if not, thanks a lot, and we pass to the final presentation, right?
Thank you, Bora.